Hi, this is ET250, lecture 23 already. Today we're going to talk about some issues when we look at the phase. Remember, we had to use that inverse tangent of the imaginary over the real part. And so there's just a slight issue that I want you to be aware of, okay? We'll look at two new equations for power that we can use when we just have a Z, if the element we're looking at is an impedance. Same with Q, there'll be two more equations. We'll kind of review in a page or two the AC power, all the fundamentals, and then we'll look at a deep dive into an example where we have a resistor and a capacitor. Okay. So let's look at these first issues with inverse tangent, okay? So let's say we have a phasor P, and the phasor has some real part and some imaginary part. And to find the phase angle, we just do the inverse tangent y over x, or the imaginary part over the real. No problem. And if it were pointed to the right or in the right half plane, this would be easy because the inverse tangent is going to get the opposite over adjacent, right? Opposite over adjacent, we get the theta, no problem. This is great if y and x are positive, especially x, right? Even if y is negative, it's okay, right? Now let's say we had y negative, x negative, right? Okay, let's see what happens, right? So let's say we have two vectors or two phasors, -3 plus 2j or 3 minus 2j. Let's see what happens. Okay, so if we convert to polar form, what do we get? Well, we get this. We get 2 minus 3, and we get 3 minus 2. Okay. And we can see here very quickly, right? So this one here with a -3 2j has an angle, a phase angle that's greater than 90 degrees. That's pretty easy to see. And we can see here that the phase of the second one is going to be less than 0, right? We have, but somewhere in between 0 and -90. Okay. And the problem is, if we just use our friend tan inverse of imaginary over real, we have either 2 over -3 or -2 over 3. But you can easily see these are going to give you the same result, -33.690 degrees. If you punch that in your calculator, you're not going to see a difference. So we can see this is good for the right one, but it's no good for the left one. Okay, so it's correct for theta 2, but not theta 1. Okay. By the way, when would you see a phasor like this? Well, you'd see it in a situation like a generator. Think of real power, negative real power, delivering power, right? Okay, but anyways, that's an aside. We'll actually see this kind of later. All right, here's the solution. What you need to look at when you are trying to compute the phase of a phasor is you need to look at the sign of the real part of the phasor. In this case, it's the -3 or the +3. And if you see that the real part is negative, you need to have a flag in your head that goes, well, I'm pointed to the left and I need to use this equation. It's the same one, I just need to add plus or minus 180. And I think you can see what I'm talking about. Look at this -33.69. To get theta 1, all I need to do is either add 180 or subtract 180. It's the same thing mathematically, right? It's your choice. Now, one way you can do it is you could then look at the imaginary part. If the imaginary part is positive, then you would add 180. And so that would give you this one. But if you chose the negative, it's still fine. Now, if the imaginary part was negative, then you could choose the -180. It would just make the number overall smaller. And what do I mean by that? Well, let's do a little example. Let's say we have the -3, 2. We have the tan inverse, we go 2 over -3 tan inverse, and we get -33.69 plus or minus 180. You can see if we add the 180, we get 146. If we subtract the 180, we get -213. Okay, so both are equivalent, right? 146 minus 213, but you might want to choose the positive version because here you have a positive imaginary part. It's up to you. Either one's the same. The point is, if you see a phasor, you're trying to get the phase, and if you notice that the real part happens to be negative, well, you got to add this plus or minus 180 to it. And I think you can immediately see it when you look at the graph. Okay. All right. Now let's look at two new equations for the real power. Remember, what is the real power? The real power is the average of the oscillating instantaneous power, right? And now let's say the element that we're looking at is a Z. Right now, we kind of have a similar situation for DC, right? If you had a resistor and a current and a voltage, we have kind of P equals IV that always works. But if you combine it with Ohm's law, you get I squared R and V squared over R. It's the same idea with complex power, right? So if you have a Z, not any element. It has to be a Z, which is a combination of resistors, inductors, and capacitors, right? Then you're going to get this equation, I RMS squared real part of Z. Notice how it looks very similar to that one. And you're going to get V RMS squared real part of Z over the magnitude of Z squared. A little bit complicated, but check this out. If you checked out the units, you're kind of getting a 1 over ohms. You're getting ohms over ohms squared, which looks very much like this equation. Okay. Now, don't forget, your Z is a complex number, which means in polar form, it has the magnitude and phase or the real part and the imaginary part. So when I see this real part of Z, I'm just pulling off the real part there. If I see the imaginary, then I'm pulling out this without the J. And if I see the magnitude, I'm just pulling out the magnitude. Okay, so yeah, these equations maybe look scary, but really they're not that bad. Okay. Now, where did they come from? It's the same idea here. You take power, which IV always works for any element, and then you add in Ohm's law, then you can get these two. It's the same thing here. So how do we know that this I squared IRMS squared real part of Z works? Well, we would take our power equation that works for any element, okay? So P equals IRMS VRMS cosine of theta V minus theta I. It's a good review from last lecture. And like I said, real power for any element. Then you apply our complex Ohm's law, not regular Ohm's law, V equals IZ. And you know that VRMS theta V equals IRMS theta I times the magnitude of Z theta Z, good. And we know that you get really sneakily two equations when you see a phasor equation, the magnitude version and the phase. And when you multiply phasors, you add the phase, theta I plus theta Z here. Okay. Now let's see what we can do. We know that this is true for any element. Can we take some of this stuff and pop it in there? Let's see. Well, I know that the VRMS for here can be rewritten as IRMS magnitude of Z. Great. Okay. So we got an IRMS, we got an IRMS, we got a magnitude of Z. Well, what is the magnitude of Z cosine of theta V minus theta I? That is nothing but the real part of Z, right? So if I had Z, for example, okay. Oh, actually drew it here, huh? If I have Z, for example, I have the real part of Z, which is the magnitude of Z cosine of theta Z. Perfect. And we know the theta of Z is theta V minus theta I. Very good, right? Theta Z equals theta V minus theta I. That goes there. Perfect. So hopefully that convinces you that this equation, P equals IRMS squared times the real part of Z, is equivalent to this one if the element you're looking at is an impedance. Okay. What about for Q? Or sorry, what about for the VRMS version? Okay, so let me put this aside. So what about this one? Again, we can start off with the same formula that works for all elements. Again, we can use complex Ohm's law, right? Boom, boom, right? Now this time we can solve for IRMS, which is just V over Z, good. And then plug that in. So what do we get? We get a VRMS divide by Z magnitude cosine of theta V minus theta. Good. So now here's a little trick, and I'm going to multiply this by 1, which is the same as multiplying it by Z over Z magnitude. And the reason why I do that is because I want this real part of Z again, right? You see that? And so now the bottom becomes a Z squared magnitude, and the top is real part of Z VRMS squared. Bang. No problem. Okay? So hopefully that convinces you that these two new equations can pair with the general equation, this one. All right. What about Q, right? So Q for a Z, well, what do we have? We have this. IRMS VRMS sine of theta V minus theta I. That's our general equation. Well, look at this. You can put IRMS squared imaginary part of Z, and Q equals VRMS squared imaginary part of Z over the magnitude of Z squared. Notice the pattern match, right? We have the imaginary instead of the real, the imaginary instead of the real. But otherwise, it's very similar, okay? So let's just write out everything together as just one kind of big page. If we have any element, and notice in all these cases, I enters V positive, what happens? We can say P equals, the real power is IRMS VRMS cosine of theta V minus theta I. This is S, the apparent power. This is the power factor. And the power factor equals cosine of theta V minus theta I, or the ratio of P over S. This is unitless, this is in watts. Then we have Q, which is the reactive power, which is what? It is the amplitude or magnitude of the component of the instantaneous power that bounces back and forth. Good. And this is IRMS VRMS sine of theta V minus theta I. We're in here. VARs. And now we have S bar, right? S bar equals S theta, where this theta is the power angle, theta V minus theta I, and S is IRMS VRMS. Good. Okay, this is just all review. Now, if an element is a Z, then we can use these two new equations, IRMS squared real part of Z, or VRMS squared real part of Z over magnitude of Z squared. If it's a Z and we want to compute the Q, you can either go IRMS squared imaginary part of Z equals VRMS squared imaginary part of Z over Z magnitude squared, bars. Good. So these are the kind of the two new equations for Z only. And why are they nice, by the way? It's because if you, here you're required to know V and I. Here you're only required to know V, but you have to know Z. Here you just need to know I and Z. Same with this one, okay? Now again, complex Ohm's law. Z is equal to the magnitude of Z, theta Z, or V over I, theta V minus theta I. Good. Now I want you to note something. This is kind of nice. The power angle way up here is the same as theta V minus theta I. If you're looking at a Z, notice the phase angle of Z is the same as the power angle. It is also theta V minus theta I. Now this only works if the element is a Z, not a power supply or anything, just a Z. But that's kind of a nice observation. The power angle is the same as the phase of an impedance. It's theta V minus theta I. Good. Nice coincidence. Okay, what else do we have? Now notice here, we have I entering the positive terminal, and all these equations are dependent on I entering the positive terminal. What would you do if we had defined I as leaving the positive terminal? Well, it's easy. You just put a negative sign and a negative sign and a negative sign. Not too bad, right? It's like the passive sign convention is coming back to haunt us, right? We have used the passive sign convention of Ohm's law for capacitors, for inductors, for steady state power, and even for this, okay? So you just need to add a negative sign. Now also, if I leaves the positive terminal, what happens for Z? You gotta put a minus sign for your Ohm's law. Okay, again, follows the passive sign convention, okay? And what does a minus sign do for Ohm's law? It is a phase shift of 180 degrees, okay? Good. What would a negative sign mean here? It would mean that you would be generating power instead of delivering power if this part was positive. What does it mean for here? You might be lagging when you're leading, or you might be leading when you're lagging, okay? And what does this mean? It means if your S is pointing one way, if you flip it, that means it points the other way, okay? All right, good. Another interesting, useful fact to know in case you want to check your math is the conservation of power still holds. So let's say you have multiple elements in the system. Well, the sum of all the real power must equal 0. All the absorbing has to match all the delivering. Same for the reactive power. All the leading elements have to match the lagging elements. Okay, so everything has to balance, and that's kind of a nice comfort. All right, so what I want to do now is kind of do a deep dive into this example. And you guys built this in lab. You hooked up a voltage supply, you had a capacitor, you had a resistor. So let's just deep dive into this system. All right, I built some simulations so we can look at some simulations, and hopefully we really get a rock solid understanding of what's going on here. Now let's say it's given that your VS is 1,000 root 2 at 0 degrees phase. So we have something that's doing this, right? And this is 1,000 root 2. When you write it like this, it's kind of telling you that VRMS is 1,000. That's kind of nice way to write it, right? This R is 100 ohms. This is 10 microfarads. And they say it's oscillating at 60 hertz, which is equivalent to 377 radians per second. Why? Because omega equals 2 pi f. And this is 6.28 or 1 tau, right? Same thing. Okay. So the question asks, please find I, P, which is the real power, the reactive power, the complex power, and the power factor for the Z equivalent. Also find the complex power for VS. Okay, good. And they also want you to draw the complex power for the Z equivalent and complex power for the VS. Good. Okay. So if we do a KVL, notice we could squish this Z equivalent together, right? That's what the Z equivalent is. And the voltage would be the same. VS here is the same as VS here. No problem. Look at this. The current's going in the positive terminal. So all those equations are fine. The positive versions. Okay. So Z equivalent has a capacitor in it. So therefore, this I better be leading this Vs, right? So we should see something like this, I leading Vs. Okay, good. So these are some things to expect. What else should we expect? Well, if we just look at the pure resistor, we should see that the power factor is 1 unity because theta Vs minus theta IR, not this I, not that I, but that I, is 0. So the voltage Vs and this current are in phase. That means the PR is going to be positive and non-zero, and the QR is going to be 0. Okay. And so if we were to plot IR and Vs on the complex plane, because we know Vs is 0 degrees at phase, and we know that the difference is 0, IR is also pointed in the same direction. Good. From the complex power plot on the same real and imaginary axis, we know that that is pointed down the real axis because this is your power angle of 0. Good. Okay, notice the difference. This is V and I on the complex plane. This is complex power on the complex plane. Good. What if we look at just the capacitor? Well, the capacitor, we know the power factor is 0. Why? Because theta V minus theta I, C, not IR, not I, but IC is negative 90 degrees, right? And that's coming from the 1 over omega C and the negative J. The real power is 0. Remember, the average of the instantaneous power for a pure capacitor is 0. It oscillates about 0. QC is now negative. It's non-zero, but negative, okay? And it's negative because QC is IRMS VRMS times the sine of this. Sine of minus 90, remember sine, what do we have? Something like this. If you take the sine of minus 90, you're going to get a negative number. So QC is going to be negative. Good. Okay, so what is that going to look like? Well, for the current and voltage, we know the current leads the voltage by 90. But for the complex power is pointed in minus 90. You see the difference. Don't get confused. So here Vs is still 0 because Vs is still the same Vs across the capacitor. We know the I leads. We know theta I is going to be greater than theta Vs by 90. And we know that SC has the power angle of minus 90. Good. Now, what about the combined system? What about the overall Vs and I, right, for the Z equivalent? Well, we know the power factor has got to be between 0 and 1. It's not 0 and it's not 1, somewhere in between. We know we got to absorb some real power, right, because we have a resistor, but we also know our overall Q is going to be negative because we have the capacitor. So it's kind of somewhere in between. So we know that the theta V minus theta I is somewhere between 0 and minus 90. So that means if Vs is pointing to the right, I is leading some, but not all the way up. And we know that S bar is not perfectly pointed down. It's not perfectly pointed to the right. It's somewhere in between. Okay. So I hope this is a summary of kind of, even before we do any math, what we would expect for all these things. Okay. What else can what other intuitions can we get before we dive into the math and look at the simulation? Well, we know from our equations, S Z equivalent, this is the apparent power, is going to be just V RMS times IRMS. Good. So once we find this, that's a pretty easy thing. We take 1,000 times whatever that number is. What about the total power of the Z equivalent? Well, there's no power coming from this guy. It's only from the resistor. So the power, the real power of the Z equivalent is actually the same as pure resistor. What about the Q? Well, the Q of this is not coming from the resistor. It's only coming from the capacitor. Bang, right? And so actually the complex power of that Z equivalent has a y-axis component related only to the capacitor and a x-axis component only related to the resistor. And you can imagine, and you guys have done this in the lab, if you were to increase the capacitance, what's going to happen? As the capacitance increases, we're not changing this x coordinate, we're only changing this y coordinate. So as the capacitor gets bigger and bigger and bigger, Q capacitor is going to get bigger and bigger and bigger. What's going to happen? You're going to have a more vertical S bar, which means that the IRMS, if Vs is constant, the IRMS is increasing, right? You're pulling more current through IC. It's becoming more and more like a short, right? Because as the capacitor gets bigger, the impedance goes down due to the 1 over omega C business, right, for the Z. Okay, so that, and I think you guys saw this in your lab, right? You get more current draw as you increase the capacitance. Okay, good. All right. So let's go over to the simulation and see if we're seeing the same thing. Okay, so I'm gonna share screen. Let's go to the simulation. All right, so here we go. We have the same system. We have a resistor, 100 ohm, 10 microfarad capacitor. I have 60 hertz voltage source of 1,000 RMS. So it's nice. In this simulator, you can actually type in RMS and it'll what do you call it? Know that it's the RMS value, not the peak. I am monitoring the current, and you might ask the question, what's that 50M? That is 0.05 amps, or sorry, not amps, ohms. And the reason why I got to put that in there is because the simulation does not like it if you have a capacitor perfectly in parallel with a voltage supply. It needs this to be able to numerically solve. So it's a very small number, but it's there nonetheless, just to make sure everything still runs, right? In real life, you always are going to have a parasitic resistor, so that's why it's okay. But for a simulation, we need to put it. Anyhow, let's run this guy and let's just see what's going on. What I want you to notice first is look at this resistor. And what do I have plotted? I have plotted the current and I have plotted the instantaneous power. Notice, as we saw in the last lecture, the instantaneous power is always positive for a resistor. And notice the colors. The colors are showing power. So the resistor is always red. For the capacitor, notice the instantaneous power. It is bouncing between positive, negative equally, right? Good. And I have the current plotted. And look at the voltage supply. Notice the current and voltage, the overall current, I. So this is yellow line is IC, this yellow line is IR, this yellow line is I. Both of these yellow lines are the same. So in this plot, we have voltage and current. And I'm going to pause it here. Notice the current is leading the voltage. Yay, that makes sense. And also look closely at the instantaneous power. Look at it's majority negative, but there's little points in time where you're getting a little kickback. So it's positive, which means this element is absorbing power, and that's coming from the capacitor. Remember, this is behaving like a spring. All right. So let's keep running it, and let's see what information we can get from here. Well, we know that for a resistor, that the Q of the resistor is 0 vars. Good. And we know that the P of the resistor has a power factor of 1. Right now, the VSRMS, because this voltage is going across all these elements, is 10,000. And that the current RMS is actually shown here. It's about 10. You guys can see it right there, 10 volts or 10 amps RMS. So the total power of the resistor is 10 times 10K times 1, which is 10 kilowatts. Okay, and I'm just using our real power formula. Okay, now remember, the power for the total system is equal to the same as the power of the resistor. So the overall Z equivalent has a power of 10 kilowatts. And I've written that right here. P cap plus pre-resistance is 10 kilowatts. Okay, let's look at the capacitor. Well, we know the average of the instantaneous is 0, therefore the real power is 0. And the Q of the capacitor is IC RMS times VS RMS times sine of theta V minus theta I. Well, we know theta V minus theta I is negative 90 for a capacitor. So we get negative 1 for the sine. We get still 10K for the VS RMS. And we get 3.7, which I'm reading off this ammeter here, this ammeter right there that's being plotted on this as the current. Okay, so this is a negative 3.7 kilovar reactive power for the capacitor. Now, if I look here of Q of this entire Z equivalent is the Q of the capacitor plus the resistor, which means that I have negative 3.7 plus 0. So the total Z equivalent has a negative 3.7 kilovar. Now, what about the total apparent power? Well, that's just IRMS here times VSRMS, right? Because that's the voltage across. So that's 10.6. If I look at this number here, see it's 10.6, 10.68, 10.7 times 10K, which is 10.6 to 8 or 10.7 kilovolt amps. All right, so I hope this whole simulation is kind of showing you that the numbers can be obtained from these plots. Now, what I want to do is a deep dive mathematically and see if we're getting the same numbers. Okay, so let's go back to the DocCam. All right, so here we are back at the DocCam. And I rewrote it here just so we have it. IRMS, that total I is 10.7, right? And you guys saw it in the simulation, all right? And that total PZ equivalent, which is the one for here, is 10 kilowatts. Good. And the QZ is coming from here is minus 3.7 kilowatts. And the totals S of this Z equivalent is 10.7. Good. Okay. The power factor is the ratio of real over apparent. So it's 10K divided by 10.7. So 10 over 10.7, 0.93. Okay, good. And what's the power factor? We know the power factor is cosine of theta V minus theta I. We know it's leading. So here's an important point. If you want to calculate the theta V minus theta I, you know that cosine is a symmetric function. So you need to choose a sign, plus or minus. If it's leading, you're going to choose the minus. If it's lagging, you're going to choose the positive. So since it's leading, we're going to choose the negative, right? So that means if I punch in a cosine of 0.936, I get negative 20.65, right? Okay, so theta V minus theta I is minus 20.65. Okay, so does that make sense? Let's look at our situation here. Are these numbers that came out of the simulation matching what we predicted? Look at this. That means this minus 20.65 is this angle here. That means that this 10.7 kilovolt amps is this length here. That means that this minus 3.7K is this length here. And that means that this 10K is this length here. The length of VS is the 1000 volts RMS, and the length of IRMS is 10.7 amps RMS. Good. What should we expect for the angle of I? Well, we probably would expect a positive 20.65, by the way. Okay, let's do a little deep dive into the math and see if we get these same results, right, that we saw in the simulation. So we go back to our system, right? So we have VS, the equivalent, I, good. And we can apply complex Ohms law. In this case, V equals IZ positive, right? Because I is going to the positive terminal, or I is V over Z, yay. This was given, but we don't know what Z equivalent is. Could we find it? We sure could. We got a resistor, capacitor, and frequency. We can see that these two are in parallel. So ZR in parallel with ZC. So it's ZR ZC over ZR plus CC. Easy. So then we can go, well, let me plug in R 1 over j omega C, R plus 1 over j omega C. And I can do a little trick, multiply it by j omega C over j omega C. That's equivalent of 1. And I get a cancellation in the numerator, and I get a cancellation here, but I got to maintain this j omega C times R. So I get this. Now, here's a cool thing I can do. Your calculator, your TI-89 will handle this. Watch this. I can plug in 100. I can put in J times 377 times 100 times 10 microfarads plus 1, and I can plug that into my calculator, and I'll actually get these numbers. 93.57 magnitude of Z with an angle of minus 20.65. Ooh, that's kind of nice. That's kind of what we predicted before, right? Theta V minus theta I is the same as the power angle, right? We got negative 20.65 from the simulation. These are good numbers. What about the real and imaginary? Well, the TI-89 will do that for you as well. 87.56 and minus 33I. Actually, let's just do that. Can you, let's see if you can see my calculator. Can I turn on the light? Can you see this? Let's see, there we go, look at that. What I can do is actually plug in, let's see, what do I have? I have 100, okay, so can we see that? Actually, you know what I can do? I can actually show you on the computer, TI-89 simulator. Let's do this. So I'm gonna go back to the computer and use the simulator to show you. So I'm gonna share screen, and let's go back to here. All right. Let's see if this works. Okay. TI-89 fork graphing calculator. Good. Click anywhere to close. All right. Does this work? TI-89 simulator. All right. Please work. Yay. Okay. So what I can do here is I can type in the numbers. Let's do it. 100 divided by, let's try it, parenthesis. Now it's J times 377. So if we look closely, where's the J, right? Do you see it here? I have to go second I, right? And then times 377, good, times 100 times 10 microfarads. I can go 10 e to the minus 6, not negative 6, plus 1. Okay, enter. Look at that. 87.56 and minus 33J. It will spit it out for you in rectangular form. Now, here's the other cool thing. I could go here and I could say, let's say we want mode. And let's say I want it now have the mode in not rectangular form, but I want it in polar form. Okay, so I hit enter. So now it's in polar form. So enter, good. And if I hit that same enter, it gives me this one. Okay. You haven't seen this form, but basically this is magnitude and phase in here. So this is 93 with an angle of minus 0.36 radians. Okay, no problem. Let's change that. Let's go to mode here and let's see if we can change it. We're going to go here and we're going to go to degrees. Okay. And I wonder if there's a way to complex form polar. I think that's okay. Let's go enter and hit it again. There it is. Look at this. 93.57 with an angle of minus 20.65. Fantastic. So now if you have the numbers, you instead of doing all this crazy math, complex math, you just plug in your TI-89. Boom. So remember these numbers, 93.57 minus 20.65. That's exactly what we got. Okay. And if I scroll up here, what was the other one? 87.5 and minus 33J. Great. Okay. So let's go back. All right, so these are the same numbers you get here. Punch in your TI-89, quick. Okay. Now I will show you later. I will show you later how would you do this symbolically. So stick around, and I'll show you, walk you through some tricks on how to do that. But I just want to get to the point right now. Okay, so let's say we want to calculate this current. Well, let's go back to the complex Ohms law, and if we want to use the complex Ohms law, we can take this 1,000 divided by the polar form, right? This divided by polar form. So if I take 1,000 root 2 over 93.57, I get 15.11 with a 0 minus negative. So I get a positive 20.65. Yes, that is what we predicted. When we got over here, we better get a positive 20.65 for that I. Fantastic. Now, if I want to convert it from amps peak to amps RMS, I just got to divide by root 2 and I get 10.7. Fantastic. Boom, got the I. Okay, let's keep going. We know it's leading, great. Theta I is greater than that. We can calculate now the power factor. Okay, so then we just do cosine of theta V minus theta I, 0 minus 20.65. We get 0.936. Fantastic. That's exactly what we got from the simulation results, 0.936. Okay, these numbers are checking out. Okay, and so we should see I going up, VS flat. VS is 0, I is up. Yay. Okay, leading capacitive. Okay, let's keep moving. All right, let's keep moving. So what about the complex power? Okay, so we know S is equal to VRMS, IRMS. Good. So that's just 1,000. And now we've already computed I. It is 10.7. Perfect. So 1,000 times 10.7 is 10.7K volt amps. Easy. Okay. Did we get that? I think we did. Yes, we did. We got 10.7 from the simulation. Fantastic. What about the real power? It's just this times the power factor, 10.7 times 0.936. That 0.7 gets killed by the 0.936. We get 10. Excellent. We're getting consistency. What about the Q? Well, S times sine of theta V minus theta I. So S times, which is 10.7 times sine of minus 20.6. I get a negative here. Good. So I get negative 3.7 kilovars. Great. We're getting the same numbers, right? So I hope you're seeing we're getting consistency from that simulation and the numbers from our equations, right? And we see that S bar would be pointed down in the fourth quadrant, 1, 2, 3, 4. Q is the equivalent, P is the equivalent, S bar. Fantastic. Okay, now let's say we wanted to avoid using the TI-89 until the last minute. And let's say we wanted to go about it symbolically, right? We wanted to just see, could we get an expression for Z equivalent, magnitude and phase, or real and imaginary, using some Phasor math? And at this point, it's just a few tricks, all right? Okay, so let's say we want to go polar rectangular. All right, so let's do the polar first because it's easier. Well, if I want to convert this to polar, I kind of done this before with the low pass, high pass filter, right? But if I'm dividing phasors, what's the easiest way to go about it? what I can do is I can convert the numerator to polar and the denominator to polar, divide the magnitude, subtract the phase. And that's exactly what it will do. R becomes R0. The denominator becomes Pythagorean theorem, right, for the magnitude, omega RC squared plus 1 squared square root. And this becomes tan inverse omega RC over 1. You've actually seen this before. Pretty straightforward. And so this becomes 0 minus tan inverse omega RC R over square root of 1 plus omega RC squared. No problem. That's the polar form of this guy. What about the rectangular form? Is there an easy way to get the rectangular form from this? Yeah, you could take this and do, what would you have to do? You'd have to find the phase and then you kind of do a cosine. This times the cosine of that, that's starting to look pretty nasty, right? Or this times the sine of that to get the real and imaginary part. That looks gross. Or you can kind of do this. This is a fun trick. Well, I don't know about fun. It's depends on your definition of fun. But yeah. Anyway, let's go with rectangular form. So here's the trick. And maybe you learned this in middle school when they introduced complex numbers to you. I don't know. But what you do is you multiply the top and bottom by the complex conjugate of the denominator. Oh, let's say that again. You multiply the top and bottom by the complex conjugate of the denominator. What's the complex conjugate? Well, you make the imaginary part negative. Why would you do this? I'll show you. Okay. It looks like this. The denominator is 1 plus j omega RC. So the complex conjugate is 1 minus j omega RC. It's okay to do this because this overall is a value of 1. So that doesn't hurt anything equation-wise. But here's what happens when I do this. The top becomes complex. It holds imaginary and real parts. But the bottom wipes out all imaginary parts. And here's what happens. Check this out. Look at this. So the top, easy. R minus j omega R squared C. Don't forget that extra R. And then the bottom does this. Look at this. I have a j times j squared. And I have the minus. Good. Omega squared R squared C squared. That's great. I have 1 times this. So that's a negative j omega RC. And I have a j omega RC times that one. That's a positive j omega RC. And then plus 1 squared. Well, look at those cross terms. They cancel. So these two j terms cancel. Nice. And what does j squared become? Negative 1. So I get a negative 1, negative 1. That cancels a positive. So I'm left with this, r minus j omega r squared c divided by something that's all real in the denominator, right? 1 plus omega squared r squared c squared, right? So the real part of this z ends up being r over this, boom, minus omega r squared c over this as well, j. This part here is the imaginary part. This part here is the real part. Cool, right? So a little trick, tell you I give you my best, right? Or I give you what you should have learned in middle school. Anyways, okay. Can we punch in the numbers? We totally could. We could use this formula and we could put in 100, 377, 100, and 10 micro. And you punch that in your calculator, you actually get 93.57. And that matches what we calculated before for the z, right? If we wanted to find the theta z, we could do a negative inverse tangent of 377, 110 micro. We get negative 20.65. Again, that matches. Fantastic. We could punch in here 100 over 1 plus 377 squared, 100 squared, 10 micro squared. We get 87.56. That's exactly what we got. And then we can do the same thing for the imaginary. Minus 377 times 100 squared times 10 micro over 1 plus 377 squared, 100 squared plus 10 micro squared. We get minus 33. These are all the numbers that we saw earlier, right? And I lost my page, but that's what we have right here. 93 here, minus 20 there, 87 there, minus 33. Now, the TI-89, I don't believe will solve symbolically for you. MATLAB and some other nice mathematics will solve nice things symbolically. But this is kind of nice, right? To be able to have the confidence to do it symbolically on your own, or to also know if I need to do quick and dirty and get a number, the TI-89 will help you do that. Okay, if we go back to the problem, let's just confirm where we're at. So we were asked for I, P, Q, S bar power factor. We've done all this, fantastic. Clicked them all out. We still need S bar for the VS and we need to draw it. So let's see what, we've already drawn this one, right? It's pointing down, okay? So let's go to this last one here. Okay, So now I've knocked this out. I've knocked this out. I just need these ones. I need the S bar, I need to draw it for the voltage supply. Well, notice the current. It is leaving the positive terminal. So all we do is just put negative signs on everything. Easy. And we've already got these numbers. Easy, right? So what are those numbers? Well, those numbers are, this is 10K and this is minus 3.7K, right? So now the new complex power for this guy is negative 10K, which means it's delivering power on the average, and it's positive 3.7K, which is kind of saying it's like inductive, right? It's balancing out the capacitive nature of the Z equivalent. Good. And what does that look like? Well, if Z equivalent complex power is pointing this way, then this is essentially the negative of that. It's just pointing the opposite direction. Nice. Okay. So I hope that makes sense. The power, you're seeing the power balance graphically. All right. The last thing is, well, what's the phase angle? What if I want S bar? I got S bar Z equivalent. It's 10.7 kilovolt amps with an angle of minus 20.65. What about this one, right? Well, what do we notice? The real part is negative. We have that tan inverse problem from before. We're coming full circle, ladies and gentlemen, full circle. And look at this. We got to add the plus or minus 180. Okay, what does that mean? Tan inverse imaginary over real. Okay, so that's 3.70 minus 10. You're still going to get minus 20, but what do you got to do? Add 180. You totally can see that we do that. 159.35. So the S of the V bar is 10.68, 10.7 kilovolt amps with an angle of 159.35. Yes, that is it. So hopefully that puts full closure on this lecture. Okay, I hope you enjoyed this lecture. I hope you learned a lot. Like and subscribe, and I'll see you in class.